In the last module, we introduced the arch P model and then looked at its properties. We saw that this model is leptochaotic and hence very often the normal distribution does not give a good fit. The T distribution is more often preferred. What we will do today is to build a arch model. Build an arch model starting from the given time series. So, generally in this case 3 steps would be involved. The first step would be to eliminate any mean non-stationarity in the process. So, we need to first look at the process and see if there is some mean non-stationarity which we can take account of through either the Box-Jenkins models or the classical model. We need to eliminate this and then look at the residuals, and the second step would be to check whether the residuals have any arch effect, in the sense that whether the residuals have some volatility in them. If so, we need to take account of this volatility and estimate the parameters of the model. In the third step, we need to go back and see if we can refine the model that we have already done. As before we did in Box-Jenkins model, it is always a question of diagnostics checking after you have fitted the model to see if the model is the best fit. The same is applicable for arch models as well, and we will be going back and checking whether the fit is good enough in the third step. Finally, what we will be looking at would be how to forecast on the basis of a fitted arch model. So, in the last module we had looked at the arch model in detail. We had looked at an arch P and we had seen the properties of an arch P through an arch 1 model. We had also given some hint of how to estimate the parameters of the model. We had seen that we can use the maximum likelihood method using either the normal distribution or the T distribution. In general, the T distribution is preferred because the underlying distribution of the arch process is leptochaotic. What we will do in today's lecture is primarily we are looking at the different steps, and as I said, there are 3 major steps in building the arch model. These steps are: we first build an econometric model, that is an ARIMA or a SARIMA model, to account for the mean non-stationarity. It is not necessary that it has to be a ARIMA or a SARIMA model. You can use the classical methods, estimate the trend and the seasonality, and then eliminate those two from the original series, and what you land up with is the residuals, and the residuals would be mean stationary in general, and hence we can use the residual series to check whether there is some volatility effect in the model. So, we obtain the residuals and test for the arch effects on the residuals. That is the first step. The second step is to identify the arch order and perform estimation. So, if we find that there is some arch effect, then we need to find the order of the arch model, and then we need to estimate the parameters of the model that we have built up. The third step is always a step that we have in time series, because time series models are alternative models would be very close to each other. So, we need to go back and check whether the fitted model is good enough, and we need to refine it if necessary. So, let us look at the 3 steps one by one. Step 1. So, we have a time series yt. This is the original series that we have. We model yt as mu t plus xt. In this, mu t is the mean of the process which evolves over time. So, this part is generally not mean stationary, and x t is the residuals. So, the smooth part is the mu t part of this is the smooth part of y t, and the deviations from this smooth part is the x t values. These are the residuals. Now, when we model y t, we model the mean of y t obviously through mu t, but this is quite obvious. But the other thing which is not so obvious is when we model y t, the variance of it, then we need to look at x t, because mu t is a constant and all the variability that y t has would be coming in through the x t component. So, first of all, we need to estimate and eliminate the mean effect, that is the mu t effect. If mu t is equal to mu, we have a simple mean which is independent of time, that is a mean stationary process, then it is very easy to actually eliminate it. So, you find mu hat is equal to y bar. We saw that in this case we have y bar which is ergodic for the mean. So, we have the ergodicity property and mu hat would be equal to y bar, and then we can very easily define the residuals as x t is equal to y t minus mu hat. On the other hand, if mu t is modeled through an appropriate Box-Jenkins model, then we can estimate mu t again as the predictor from that model. So, we can fit in a ARIMA or a SARIMA model and then predict the mu t value. In that case also we can then find the residual as y t minus mu t hat. And now we need to fit or check first for a variance non-stationarity or volatility of the residuals x t. If there is non-stationarity in the variance of x t, then we need to fit a appropriate volatility model, and the simplest of them would be the arch model. So, this is the first thing that we need to do. So, suppose we assume that we have estimated mu t and eliminated it. So, now instead of y t we have x t. Now, we need to check whether there is heteroscedasticity in the x t's. This is done through what is referred to as the Lagrange multiplier test, which was proposed by Engel in 1982 when he actually proposed the arch model. This is a very simple test. So, what we have is an arch model, x t is equal to epsilon t sigma t, and sigma t square is dependent on its past values. You can replace the sigma t's by x t squares as well, and we test for alpha 1 equal to alpha 2 equal to alpha p. Now, when you do this, you need to have an alternative. So, the alternative is that all the alphas are not equal. If some of the alpha j's, j running from 1 to p of course, are not equal to 0, then there is some dependence in the past, and we will say that there is an heteroscedastic effect. Assume that epsilon t is to be IID with mean 0 and variance 1. Now, in the Lagrange test what you do is, since the sigma t's are unknown, so what we do is we use x t's instead of the sigma t. So, you can use x t instead of sigma t and write the model this way. And then what you do is you regress the x t square on the past values, square of them. So, you regress them on x t minus 1 square, x t minus p square, and then estimate the alphas simply by the ordinary least square method. And if you do that, the residuals would lead to the unrestricted sum of squares as URSS. URSS is primarily the square summed of the residuals. So, you square up the residuals, which is x t square minus the estimated predictor x t hat square and take the sum, and you get the unrestricted sum of squares. As opposed to this, suppose we have the hypothesis to be true. In that case, sigma t square becomes equal to alpha naught, and you get, regressing this, you get a very simple restricted residual sum of squares as x t square minus the mean of the x t squares, because alpha naught hat would be the mean of the x t squares. So, that would be the fitted model, and you get the residuals as x t squares minus that, and the square sum of this would give you the restricted residual sum of squares. And the F statistics, as usual, is constructed as RRSS minus URSS by URSS divided by the corresponding degrees of freedom. And this follows an F distribution with parameters or degrees of freedom p and n minus p minus 1, and you would be rejecting H naught at the alpha % level of significance if the observed value of f is greater than the f alpha value. So, if you accept, it means that there is no heteroscedasticity, it is homoscedastic, and if you reject, you know that there is heteroscedasticity in the model. Some of the alphas are not equal to 0, and hence there is some dependence on the past. So, having done this, and suppose we find that the null hypothesis is rejected, that means there is heteroscedasticity, and we want to fit a arch model. So, the first thing that we need to do is to identify the order of the arch model. How do you do that? Now, the variance of the model with x t square in place of sigma t square is, if you look at this, this is an ARP, and it is thus expected that x t square will have an ACF which will be asymptotic to the h axis. So, we are usually what we look at is x t, but now we are looking at x t square as the process, and if the ACF is asymptotic to the h axis, it is not going to be a moving average process. And if the PACF is 0 beyond some point, then we can say that if that point basically is the order of the process. This is exactly how we identify the order of a ARP process. We look at the PACF, see where it becomes 0. Suppose it becomes 0 at 10, then we know that the order of the process is 9. So, we can use the same technique using x t square instead of x t in this case. So, as soon as it becomes insignificant, mind you, it is not going to be exactly 0, but as soon as the PACF becomes insignificant, you choose p as the order. Then what do you do? Having chosen the order, you need to estimate the parameters of the model. Now, we have assumed that x t is normal 0 sigma t square. In that case, we know how to do it. We saw this in the last class, and we also said that more preferably we would rather take the t distribution with new degrees of freedom and variance sigma t square rather than the normal distribution, because the underlying process is leptocartic. And we saw that if you use the maximum likelihood method to obtain the parameters for the t distribution with nu known, the log likelihood for the t distribution would come out to be of this form. So, if nu is known, then there is a component, large component with nu, which would be absorbed in the constant. We need not estimate that. So, that would be known to us, and we are simply interested in looking at the second term on the right hand side, which is the summation term, and we can estimate the parameters alpha naught from this. Remember that alpha naughts do not come out directly here, they are embedded in the sigma t squares. So, sigma t square is in terms of the alpha j's, and once we write those out, we need to differentiate L first with sigma t square and then with respect to the respective alpha j, and then we can use the score vector and the Fisher information to estimate the parameters. On the other hand, very often what happens is nu would be unknown to us. If nu is unknown, then it needs to be estimated as well. So, what we do in this case is we do not discard the constant part which involves nu. It also involves certain other things, but mostly it involves nu, and we write the likelihood, full likelihood this way. So, you look at the first term here, it is primarily a term which concerns nu, and we will need to incorporate this. This becomes a little bit more complicated, and because nu is involved in this term as well as the original term on, that is the second term we have here on the right hand side. So, we need to estimate with or take the derivative with respect to both nu and the alpha j's, which should be embedded again in the sigma t squares, and then we can find the estimates both of the parameters as well as the parameter of the underlying distribution t. Now, very often what happens is that we are using a t distribution because it is heavy tail, that is it is leptocartic, but also often the underlying distribution is skewed. In such situations, very often one looks at a skewed t distribution. Now, this can come in several forms, but we will not be discussing here. But I want to mention is that if you have a heavy tail distribution which is skewed, you can still account for it. So, you should be looking at a more appropriate distribution, but the technique of estimation would be the same. That is, you write down the likelihood in terms of whatever distribution you get. Obviously, a skewed t distribution in whatever form you write it will be much more complicated than either of these two, and then you need to estimate the parameters as before. That is, you get the score vector, you get the Fisher information, and then you use the method of scoring, and you get the estimates of the parameters iteratively. So, this is how you can estimate the parameters. Having done this, so what we have now is we have got the order, we have got the estimates of the parameters. So, we know the whole model. Okay. Next is we will need to look at the adequacy of the underlying model. What does this mean? Means that we need to check whether the model that we have used is good enough or not. Now, first of all, define the standardized residuals, because the residuals are the ones that you generally check the model through. Okay. And in this case, we have epsilon t hat is equal to x t by sigma t hat. Remember, our model was, the first equation was x t equal to epsilon t into sigma t. So, epsilon t hat would be x t divided by the estimated sigma t. Since we know the alpha j's, we get the estimate for sigma t. And then this should be either a normal distribution or the t distribution, because those are the underlying distributions that we have been looking at. So, how do you check? Either you check this through the skewness and the kurtosis, look at what the skewness and the kurtosis values are like. You know that the normal distribution is symmetric and mesocartic, whereas the t distribution generally is symmetric, but can be leptocartic. The t is itself symmetric and leptocartic, but then, as we said right before, we can have a skewed t distribution as well. So, we need to check whatever skewness and kurtosis that we are assuming, whether this holds. The other very simple way to do it is to look at the QQ plot. So, we do the quantile plot and see if it comes out to be a straight line, which would indicate that we have a reasonably good fit, and the model in that case would be adequate. Now, let us see how we can forecast on the basis of this model. So, what we have is, we have identified the model, we have estimated the parameters of the model, so we know the model very well now. So, what do we build the model for? For forecasting purposes. So, how do you forecast on the basis of the given model? So, suppose we are given x1 to xn. So, suppose n observations are given and we want to predict further ahead. So, we want to look at n plus 1 or n plus 2, etc. So, looking at n plus 1 is simple, it is a one step ahead predictor, and sigma n plus 1 hat square would be alpha naught hat, alpha 1 hat x n square, etc., alpha p hat x n minus p plus 1 square. This is simple because we are just using the estimated alphas and all the x's that we require. Sigma n plus 1 depends on x n, therefore, and its past value. So, this is all given. The problem comes in when we look at further steps. So, let us just explain this to the two step ahead predictor. Now, what we have is sigma n plus 2 hat square, and this is alpha naught hat plus alpha 1 hat, it should have been x n plus 1 square. But we do not have an x n plus 1, mind you, we just have x 1, x 2, x n. So, what we do here is instead of x n plus 1 hat or x n plus 1 square, we use sigma hat square n plus 1 as a substitute. Plug this in, the next one is x n square. So, it does not create a problem because the x n is something we know and the remaining are even further past values. So, the remaining values are fine. You can guess that if you go for a 3 step ahead predictor, sigma n plus 3 hat square, then the first two terms would have x n plus 1 and x n plus 2, which would be unknown, and hence we will need to plug in the predicted values there, and the remaining values we already have x values. So, it can be done. So, this is how we actually forecast on the basis of the model that we have fitted in. Just remember that this is the forecasting for the x's. If you want to forecast for the y's, then obviously it would be the sum of the two forecasts. So, you will have to forecast from the mu t value, that is the mean part, and you forecast from the variance part through the x's, and then you take the sum of the two forecasts to forecast for the original y values. In today's class, we have seen how to build a arch model. Starting from a given time series, we have seen that if the time series consists of some mean non-stationarity, that is, there is some trend or seasonality, then we should take account of that through either the classical models or the Box-Jenkins models. And after eliminating this non-stationarity in the mean, we need to look at whether there is volatility in the residuals. We saw that if volatility is present, then how we actually fit a arch model. First of all, how we test for the arch model through the Lagrange's test, and then how we estimate the parameters of the model if there is a arch effect. Finally, we saw how we predict on the basis of the fitted arch model.